Second kind of curvilinear coordinate system that is often employed in analyzing the motion of particles along the curve path is called polar coordinate system. Okay, so polar, also called r theta coordinate system. So what is a polar coordinate system? In a polar coordinate system, the position of a particle moving along a path, whether straight or curved path, is given by two variables. Okay, so here is, let's say, particle P, then its position is given by the distance from the origin, we'll call it r, as well as an angle that this line makes from horizontal, let's say. And you can pick, what would be the reference line. We can pick the x-axis, let's say, and theta in this case is possibly this way, or I could pick my theta going from the y direction. That isn't, that could happen as well. It's not a problem. Okay, but the theta always has to be an increasing theta direction, so that has to be positive theta direction. So when we do this, then we also pick two unit vectors. One we will call er hat. So er hat is a unit vector that points radially outward from the point O, from the origin. So er hat is the direction in which r would actually increase. Okay, and e theta hat would be another unit vector perpendicular to er hat. So perpendicular to er hat, and e theta hat points in the direction that theta is actually increasing. So this is the direction that theta is increasing. So that's why the e theta hat points that way. Don't make the mistake of making the e theta point this way, because in this direction theta is actually decreasing. Okay, so please don't do that. I'm going to just erase this. So, on the other hand, if let's say I pick my theta and I'm going to draw the same path over here, and here's my particle P, and I'm going away from the origin, so that's my er hat and that's my r. If I pick my theta to be going this way, so if my reference axis was y, and you might see that in some of the problems, then e theta hat actually points this way, because that's the direction that theta is increasing, because you pick your y-axis to be your reference line. Okay, so the direction of er hat would be always radially outward, so that r is increasing, and e theta hat would be perpendicular to er hat, but perpendicular would be two directions in a plane, so you would decide which way it would go by looking at which way theta is actually increasing. Okay, all right, so in polar coordinate system, the position of a particle is given by the distance, which is the magnitude part of the position vector, and the unit vector along radial direction, right? So r is given as r hat. Okay, so this is our starting point. So if this is the starting point, then what is the velocity? D over, sorry about that. D over dt of r, which is d over dt of r hat, right? So this is, product of two functions, so that will be dr over dt times er hat plus r times d over dt of er hat, right? So this is r dot er hat, and this is r d over dt of er hat. Now what is this quantity? Okay, this is nothing but, again, derivative of a unit vector. We already know what the derivative of a unit vector looks like. So d over dt of a unit vector is given as theta dot k hat, which tells you the rate at which the u hat is changing its direction across the unit vector itself, right? So if we use this relationship for er hat, what do we get? We have d over dt of er hat equal to theta dot k cross er, right? Okay, so that's what we get. Now k hat is actually a vector that's pointing up, right? Because if theta dot is increasing, then k hat is pointing up. Theta dot is going, k hat is pointing perpendicular to er hat and e theta hat, right? So er hat, e theta and k hat, they form a right-handed coordinate system, right? So k cross er would be equal to e theta hat. So this is actually equal to theta dot e theta hat, right? So let's substitute that in here, and we get r dot er hat plus r theta dot e theta hat, and that's the velocity expression in r theta system, right? So it has two components. It has r dot, which is the radial direction component, and it has r theta dot, which is the theta direction component, right? So that's how we get the velocity. What about acceleration? Let's get that as well. So acceleration is defined as dv over dt, and that would be d over dt of this whole expression. So that's r dot er hat plus r theta dot e theta hat. Okay, now this is going to be lead to a sort of bigger expression. So I'm going to start from the left. So we have r double dot er hat plus r dot d over dt of er hat, and that's basically the derivative of this term over here. Okay, so this is the first term, this is the second term. Okay, plus we have the derivative of the second term now, so we will have let me write this first, d over dt of r theta dot times e theta hat plus r theta dot. I'll treat r theta dot together right now, d over dt of e theta hat. Okay, so let's write the first term as it is, r double dot er hat plus r dot. What is d over dt of er hat? Well, d over dt of er hat we just saw is equal to theta dot e theta hat. So write that theta dot e theta hat plus this would be, second would be r dot theta dot plus r theta double dot e theta hat plus r theta dot d over dt of e theta. What is d over dt of e theta? So let's look at that. D over dt of e theta is equal to theta dot k cross e theta. Okay, and k cross e theta is minus er, so that's minus theta dot er hat. So let's substitute that, minus theta dot er hat. Okay, now we've done all the derivatives, so let's collect all the terms. So I'm going to collect all the coefficients of er hat first. So we have r double dot, we have minus r theta dot square right here, minus r theta dot square, and that is coefficient of er hat, plus r dot theta dot, r dot theta, so that's 2r dot theta dot plus r theta double dot e theta hat. That came from here, right? So that is the expression for acceleration. So let me write this again. Acceleration is equal to r double dot minus r theta dot square er hat plus r theta double dot plus 2r dot theta dot e theta hat. And that's the expression for acceleration in r theta coordinate system. Okay, so this looks like a big term, right? So let's try to understand it. That's very important too. Again, we have two components of the acceleration, one that's pointing along the radial direction, the other that points along the theta direction, right? So we can write this as acceleration along radial direction er hat plus a sub theta e theta hat, where ar is equal to r double dot minus r theta dot square, and a sub theta is equal to r theta double dot plus 2r dot theta, right? So along a curved path, this is the curved path that was the coordinate system. You have the particle p here. We know that the velocity is always tangent to the path, right? But in the r theta system, you have radial direction er hat, and you have the theta direction. Okay, so this is my r, this is my increasing theta. Velocity can be resolved along er direction as well as e theta direction, and we've seen that along er direction, velocity is r dot er hat, and along theta direction is r theta dot, right? So it has two components too. So velocity can be resolved along radial as well as theta direction. Okay, and it will be easy thing to do if, let's say, you knew the velocity and the angle it was making from, let's say, radial direction, it was, let's say, theta prime. You could resolve it along r direction and theta direction. Similarly, the acceleration also has component along radial direction as well as theta direction, given by these two terms over here. So how would you solve problems? Well, the problem may be that you are given r as a function of time, you are given theta as a function of time, and you may be asked to compute the velocity as well as acceleration. So let's do a simple example, a straightforward one. So let's say you were given r as a function of time to be 2t square meters. Okay, and you are given theta dot as constant, let's say 5 radians per second. Now remember, every time you have to write theta dot or theta double dot, make sure that it is always in radians per second or radians per second square. Never use degree per second or anything else for computing theta dot or theta double dot. So we know r, we know theta dot, right? Theta dot is constant, so theta double dot would be equal to 0, right? Okay, r is known, so we can compute r dot, that will be 4t. R double dot can also be computed, that will be, sorry, this is just 4t, 4t, and r double dot would be 4, right? So now we have r double dot, theta double dot. We can compute the velocity. Velocity is r dot er hat plus r theta dot e theta hat. R dot is equal to 4t er hat plus r is 2t square, right? And theta dot is 5, so that's 5 e theta hat meters per second. So everything is a function of time. So if you're looking for velocity at any given time instant, you can substitute that t value in this expression and get the velocity, right? What about acceleration? Acceleration is given as r double dot minus r theta dot square er hat plus 2r dot theta dot plus r theta double dot e theta hat, right? So r double dot is 4, so that's 4 minus r is 2t square, so 2t square times theta dot square, that'll be 25, so that's er hat plus 2r dot is 4t times theta dot, which is 5, plus r is 2t square, and theta double dot is 0, so that's actually 0, so this will drop out and we'll get e theta hat. So what do we get? We get 4 minus 50 t square er hat plus that will be 40 t e theta hat, and that will be meters per second square, let's say. So again, if you want to compute the acceleration at any given time instant, you can substitute for that time value and get the acceleration from that.